Hi Calc 2 people, welcome to Chapter 9, Differential Equations. The first section we're going to talk about in Chapter 9 is modeling with differential equations, or just an introduction to differential equations. First of all, what is a differential equation? A differential equation is an equation that involves the derivative of an unknown function. So it's an equation that involves the derivative, at least one derivative of, let's say, an unknown function. Make that an unknown. A differential equation, so from this point forward, I'll abbreviate differential equation DE. A differential equation, is considered solved when we find this unknown function or set of functions that solves or satisfies the equation. So our goal is to discover or find the function that satisfies the equation. So a differential equation is considered solved when you discover the function or set of functions that satisfy the equation. That is, if there is, in fact, such an equation exists. So today we're just going to look at the basics of differential equations, get a feeling of what a differential equation is, and see how we can check to see if a particular function is a solution to the differential equation. So let's look at this differential equation. We have to get comfortable with the notation. So y equals y prime. We're assuming our function is y. We don't know exactly what the input variable is. So in situations like this, you can either use x, y is a function of x, or y is a function of t. But what we're looking for is a function who in fact equals its derivative. So y is the unknown function. And can you think of a function whose derivative is itself? So this is just a matter of thinking back to our calc days and derivatives. How about y equals e to the x? So this is actually one solution. Right? So this is one solution, y equals e to the x. And we can check. If y equals e to the x, then its derivative is e to the x. And does y equal y prime? Well, of course, e to the x equals e to the x. So I see that's one solution. Another solution. How about y equals 4e to the x? Let's check. The derivative of 4e to the x is 4 times the derivative of e to the x, which is 4e to the x. And we can clearly see that y equals y prime. Yes, 4e to the x equals 4e to the x. So notice I could have changed this number to 14. In fact, I could put any constant here, 614, and its derivative is going to equal itself. So the general solution is any function y equals a constant times e to the x. And you can check this because the derivative of a constant times e to the x is always equal itself. So now, we have a situation here where we have two letters involved. Well, actually, we have three, but E is really a number. C is a constant, X is a variable. So how are we to know this? Well, it's typically understood that X and T's are our input variables. Y is typically our output variable. It's not always the case, but that's what we assume if it's not told. And then the constants are usually indicated with letters that are at the beginning of the alphabet. So I'm going to assume C is a constant. So now this differs from these two, even though they're all solutions. So here, my constant that we don't see is 1. Well, we have here what we call particular solutions. Particular solutions. Particular solutions is when there is an actual value of this constant assigned. So here the constant would be 1, here the constant would be 614. This one is called a general solution, saying that this is true in general for any constant C. So just watch the directions carefully. Do we find a general solution or are we looking for a particular solution? Well, that depends on the information that's given, and we'll get to that in a moment. So general solution involves unknown constants because this is actually what we call a family of functions. It's an infinite collection of functions. Y equals any constant times e to the x will solve the original differential equation. And here are two particular examples from that infinite collection in that family of functions. All right, let's look at another differential equation. 4x squared times y double prime, that's double prime. Maybe I should make those on an angle more. Let's do it this way. Double prime plus 12x times y prime plus 3 times y equals 0. Seeing the derivative is put on the y, and typically we assume y is going to be our unknown function. This is what we call a second order differential equation. The order is determined by the largest derivative present. In the differential equation. So we would call this a second order because of the second derivative right there. If we go back to this guy, the highest derivative is just the first derivative, so this would be a first order differential equation. So this is a second order differential equation. Y is considered our unknown function. So let's show, I'm going to tell you the solution, or a solution, show y equals x to the negative 3/2 is a solution to the above differential equation. All right, well, we start with our unknown function, x to the negative 3/2, y equals x to the negative 3/2. We need to find its derivative and its second derivative. So y prime, bring the power out front. Oops, drop the power by 1, negative 5/2. And the second derivatives bring the power out front, so it's going to be 15/4, x to the negative 7/2. Now where we see y, we're going to put x to the 3/2. Where we see y prime, we'll put negative 3/2 x to the negative 5/2. And where we see y double prime, we will put 15/4 x to the negative 7/2. So we want to see if, in fact, that this all balances out on both sides of the equation. So 4x squared times 15/4 x to the negative 7/2 plus 12x. The first derivative would be negative 3/2 x to the negative 5/2 plus 3 times x to the negative 3/2. And does that equal 0? Well, let's just do the algebra here. 4 times 15/4 is 15. X, well, add 2 to negative 7/2, so that's negative 3/2. 2 plus negative 7/2 is negative 3/2. 12 times negative 3/2 would be negative 18. And then it would be x. Well, 1 minus 5/2 would be negative 3/2. Plus 3 x to the negative 3/2. And look how nicely that worked out If we have 15 of something and we subtract 18, we're at -3. We add 3, we get 0 equals 0. So this is a solution to this second order differential equation. Now notice I told you what the solution is. Differential equations itself, there's many ways to solve differential equations depending on the type of differential equations it is. There's courses offered for you to take, many courses you can take just in solving differential equations. So here, I'm not telling you how we got this solution. It's beyond the scope of what we're doing right now. But what I want you to do is get the idea of what a differential equation is and be able to show that this is in fact a solution. So y equals x to the -3/2. Now notice there's no random constants involved here. So this is a particular solution to this differential equation. I want you to note that I think y equals x to the -1/2 is also a solution to 4x squared y double prime plus 12x y prime plus 3y equals 0. And what you can do for practice to do is to check this. So those are particular solutions to this differential equation. So take y equals -1/2, x to the -1/2, sorry. Repeat the process and show that it balances out this equation, just for practice. All right, so how do we know what solution we're looking for? If we go back here, are we looking for this guy, or are we looking for that one? Or are we looking for e to the x, 614 e to the x, or are we looking for 10 e to the x? How do we know? Well, in order to determine specifically what we're looking for, we need some additional information. We have what we call initial conditions. It's a set of conditions. It's a condition or a set of conditions. So a condition or a set of conditions that allow us to determine which solutions we are after. Okay, they are the values of the solution or its derivatives at specific points. I'll just write that down. The values of the function, FCN is my abbreviation for function, or its derivatives at specific points. And we'll see an example of this in a moment. A differential equation plus initial conditions is called an initial value problem. So an example of an initial value problem, let's suppose we have y equals y prime. And let's suppose we add the condition y of 0 equals 4. So this is called an initial value problem. We have the differential equation, and then we have something about the function that will help us solve for the value of c. Well, we already know the general solution to y equals y prime is y equals any constant e to the x. But this condition right here is going to help us find the particular solution. When we stick 0 in for the output, the output has to be 4. Well, y of 0 is c e to the 0, and that has to equal 4. So now we solve this little itty bitty equation. E to the 0 is 1, so c has to equal 4. So therefore, the particular solution to this initial value problems force us to find the value of that arbitrary constant. Therefore, the solution to the initial value problem, y equals y prime, y of 0 equals 4, is y equals, and we're going to replace c with 4 e to the x. So this satisfies both these conditions. Its derivative is itself, and when we plug in 0, the output is 4. All right, let's practice another one. Let's show this is a little more complicated. Let's show that y equals 3/4 plus c over t squared is the general solution to this differential equation. Now notice here, my input variable is always indicated in parentheses. Output variable is going to be y here. C is my arbitrary constant. So if y of t equals 3/4 plus c over t squared. When I take derivatives, I like to get things out of the denominator, so I'm going to write this as ct to the negative 2. Then the derivative, it's a first order differential equation. I only need to know the first derivative. So the first derivative is, well, the derivative of 3/4 is 0, and the derivative of a constant times t to the negative 2 is negative 2c t to the negative 3. Okay. I'm going to now write this as negative 2c over t cubed, and I'm going to put it back into here. 2t y prime plus 4y equals 3. Y prime is going to be 2t, so I'm going to replace y prime with this right here. Negative 2c over t cubed. Oops, I lost. Plus 4 times y, which is the original function, so I go back up here, and I'm going to put in 3/4 plus c over t squared, and does that equal 3? Well, let's do the math. 2t times negative 2c over t cubed is negative 4tc all over t cubed, plus 4 times 3/4 is 3, plus 4 times c over t squared, 4c over t squared. Does that equal 3? Well, 4tc over t cubed, these t's cancel. One of the t's, the t on the top cancels with one of the t's in the bottom. So this is showing a check of this differential equation. We were told the solution. Sorry, I was a little crooked there. Now notice negative 4c over t squared and positive 4c over t squared cancel. We get 3 equals 3. So this is in fact a solution to this differential equation. So this is a general solution because it involves an arbitrary constant. All right. Let's look at the next problem. It says find the particular solution to the initial value problem, 2ty prime plus 4y equals 3, y of 1 equals negative 4. Well, for 2t y prime plus 4y equals 3, we already know the general solution is y is equal to 3/4. From the previous page, I told you the general solution. So in this section, we're not learning how to solve differential equations. We are showing how to show that a solution is in fact a solution to the differential equation. So this is the general solution. We checked in the last page that this in fact satisfies this equation. Now we have the initial condition. The initial condition is that when we put 1 in for the input, negative 4 is the output. So y of 1 would be 3/4 plus, now remember, c is just a constant. The input variable is t, so it's 1 squared, and the output's going to be negative 4. So now we solve this for c. 3/4 plus c over 1 squared is just c equals negative 4. Let's do that instead. C equals negative 4 minus 3/4. So that's negative 16/4, which is negative 19/4. So therefore, the particular solution to the initial value problem above is, I'm going to get it onto the next page because I'm running out of room here. Y is equal to 3/4 plus negative 19/4 all over t squared. But we would never leave it like this because we don't leave fractions and fractions. 3/4 minus 19/4t squared. There we go. All right, so have fun practicing some of this stuff. What you're going to do is read 9.1 in your text. Exercises 1, 3, 5, 7, 9, A and B, and 13. And then your XYZ homework, which is due next week. Oh, let's see, did I write that down? Oh, 4.1, I did. Ah, yay. 4.1 problems. All right, everybody. Have a good day. Talk to you later.